So far in this class, we've talked a lot about solving ordinary differential equations, first-order ODEs, second-order ODEs, and different techniques that we can use to solve them. Power series, Laplace transforms. Starting today, we're going to start solving partial differential equations, and in particular, PDEs that are bounded across a finite domain. We just learned about the Laplace transforms. It's very useful for unbounded domains. For example, initial value problems. You start at some time t equals 0, and that time shoots off to infinity because you integrate from 0 all the way to infinity. So it's very useful for initial value problems where the domain, like time, is unbounded. But in many problems in science and engineering, you have bounded domains. For example, if I wanted to calculate the heat transfer across this room, it's a bounded domain. The walls don't jet out to infinity. It's bounded from negative L to L if origin is right in the middle, right? So we want a technique where it's useful for a bounded domain. And Laplace transforms isn't the best for bounded domains. We're going to start learning today Fourier series, which is exactly the technique that's oftentimes useful for bounded domains in partial differential equations. These are oftentimes called boundary value problems. So let's talk about the Fourier series. It's a new way to express a function over a finite domain from x going from negative L to L. I'm just going to write down one possible case of the Fourier series using sines and cosines. It looks just like this. Now, it looks very complicated to you, but let me explain what we're doing philosophically. Suppose you have some function f of x. And let's suppose that function has some property between negative L and L. And that plot looks something like that. Okay? And we have f of x. And the idea behind the Fourier series is you're going to take that function f of x and express it as a bunch of summations of individual sines and cosines of different frequencies. Okay, so just defining things here. L is the size of the domain. It goes from negative L to L. X is your independent variable that runs along the x direction. And pi is the usual pi from the equation of the circumference or area of a circle. And the a sub 0, a sub n, and b sub n are called weights or coefficients. They tell you how much of each cosine or sine that I want to grab in order to model this function most accurately. So the idea behind this is we're going to take an individual cosine wave, for example, one cosine wave, that might look something like this. So that would be something like cosine of 1 pi x over L, because it does one full oscillation between the bounds of negative L and L. And there's going to be a coefficient that comes out in front of that, which tells you how much of that particular wave I want to take in order to reproduce this full function f of x accurately. Obviously, this function f of x, shown here in blue, and the pink curve shown in cosine 1 pi x over L doesn't match up so well. So what we're going to do is add to this another different type of cosine or sine wave. For example, in yellow, I've shown here a different sine wave about sine 2 pi x over L because it does two full oscillations between negative L and L. It's not just about 2 pi x over L, it's exactly sine 2 pi x over L. And the idea is we're going to add together this pink curve and this yellow curve together and see if it's even a little bit closer to representing the full function f of x shown in blue. And you keep doing that for more and more values of n, also called the index, or called the mode number. I'm going to take the mode of n of 1. I'm going to take the mode of n of 2 for both cosine and sine and add up many, 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 many of them all the way out to infinity to see if I can reproduce the original function. So you're just taking a bunch of individual waves, adding them together in just the right way to see if we can build up our original function f of x. Now there's one minor detail of why the a sub 0 term is outside the summation. This has to do with a technical definition of the specific mode of n of 0. For cosine of 0, this value becomes 1, and therefore the coefficient a sub naught has a factor of 1/2 that comes outside. And depending on how you define that coefficient, that factor of 2 might be absorbed into the a0 or just be taken explicitly outside. That's a minor technical detail. I wouldn't worry about that so much. For now, just think of this as I have some complicated function of x, and I want to represent that by adding together a bunch of sines and cosines. Now, it all comes down to what is the weight, a sub n and b sub n, for each mode, for each wave that I have. How much weight do I carry? I like to think of it as kind of like a piano. On a piano, you have a bunch of keys, and each time you press a key, it activates a string. There's a little hammer, it hits the string, and the string vibrates. And it spits out a particular frequency based on the length and the thickness of that string. Now, musical instruments are a little bit more complicated. There are concepts of timbre, which complicates things a little bit, but let's not worry about that. Suppose that each key, each string on your piano is one specific frequency that it outputs. Maybe a cosine, right? A 440 hertz is 440 oscillations. Now, for that one key, you want to figure out how strongly do I press that key? And I'm going to combine that key with other keys. And if I play them in just the right balance of the different strings and keys, I might be able to create a beautiful piece of music or a beautiful function. That's kind of morally the principle behind the Fourier series. Of course, like I said, musical instruments are pretty complicated, so it's not explicitly and strictly that way, but it is a good analogy to make with regard to the Fourier series. So now, it comes down to what is the coefficient a sub n and b sub n? That's really what it comes down to. If we can figure out what the weights are, then the Fourier series will be very easy. Now, recall the power series. In the power series, we tried to find a solution that was a summation of a bunch of weights multiplied against a polynomial, x to the n. And we figured out how you find the c sub n based on recursion. And that was how we found the weights. Same moral concept over here. We want to find somehow, using a clever technique, to find the weights. And a very important point that we're going to make here is going to help us how to find the weights. Because when you just look at something like this and see this equation, it seems extremely challenging to figure out what the weights might be. It would be unthinkable for me to imagine, okay, I want sine 3, I want sine 4, but I wouldn't know how much of those to add and what ratios to make some arbitrary function that I have. Now, the concept that's going to become very important to us is called orthogonality. So let's think about orthogonality. Okay, the concept of orthogonality says that two functions, g of x and h of x, are orthogonal over the domain negative L to L if and only if the integral of negative L to L of the product of those two functions integrated over the area under the curve is equal to 0. This is the definition of orthogonality. Now, you might have known about orthogonality in the context of vectors. Two vectors are orthogonal. They're orthogonal if the dot product between those two vectors are 0. This was the definition of orthogonality in vectors. Now, it turns out functions can also be orthogonal, and this is the definition of what it means for two functions to be orthogonal to each other. Now, let's think about orthogonality in the context of sines and cosines. It turns out that sines and cosines are extremely special functions. They're not just ordinary functions like polynomials, which are not special functions. Sines and cosines are special. And the reason why they're special, and you might have been wondering, why do we choose sines and cosines for Fourier series? It's specifically because of this property. Now, it turns out that if you take sine and cosine, multiply with each other, integrate it between negative L and L, a very unusual thing happens. Let's suppose you have these two functions. G of x is equal to cosine n pi x over L, and h of x is sine m pi x over L. So m is a different index, or it can be the same as n. And remember, n or m are integers. They're integer values because you're summing from n of 1 all the way to infinity. So they're both integer values, and m and n can be any integer. Now, it turns out that when you multiply cosine and sine together and integrate from negative L to L, a very interesting thing happens. So let's take a look. OK, so interestingly, when you take the integral of cosine n pi x over L, multiply it with sine m pi x over L, integrate it from negative L to L, you always get 0, regardless of the value of n or m. You always get 0. Let's make things concrete, because I think m and n seems to spook out some students when I first show them. So let's make things concrete. So let's say I have sine cosine 3 pi x over L, and I have sine 5 pi x over L. I'm integrating those two things. It just gives me 0. It's a little hard to think about because you're plotting a cosine wave and a sine wave, and you're taking the product and the area under the curve. Because primitively, that's what we're doing here. We're taking the area under the curve. We're taking the area under the curve of the product of a cosine and sine. And you can keep doing this. You can do this for any value. It's always going to be 0, even if n and m are the same. So if it's the same, n equal 2, m equal 2, you're always going to get 0. Okay? No matter what combination of n and m you have, you're always going to get 0. Okay? This means that cosine and sine are always orthogonal between the domains negative L and L. Okay? And the same is true for the opposite. Obviously, if g of x is equal to sine n pi x over L, h of x is cosine n pi x over L, you're also going to get always orthogonality. Now, the very interesting case is when you have cosine multiplied with another cosine. Okay? So when you have cosine n pi x over L times cosine m pi x over L. So let's try that for a couple of numbers. So I'm just literally going to change this to cosine and another cosine product. I'm going to choose here 2 pi x over L times cosine 5 pi x over L, bounded between negative L and L. That integral, turns out, is also equal to 0. I'm going to change the values. If I make it cosine of 20 times cosine of 5, it's still equal to 0. Okay? But when the values are the same, we should check that too. So let's see. Cosine of 5 pi x over L times cosine of 5 pi x over L. In this specific case, what we find is that the product of those two functions is not equal to 0. It's equal to L. Okay? So apparently, when cosine of n pi x over L and cosine of m pi x over L, if the n and m are the same number, we get a non-zero value. Same thing for any value, right? You can just put any value. If they're the same numbers, what you get is that it's non-zero and it's always equal to L. Let's try the sines. Sine of 10 pi x over L times sine of 9 pi x over L. It's equal to 0. It's always true. So sine and sine is also always equal to 0, except when the two values are the same, you get L to come out. So we're picking up a trend here. It turns out that these two pairs these two pairs, are always orthogonal. But when you have these pairs, it's orthogonal when n and m are not equal to each other. And when they are, you get the value of L. OK, that's all I wanted to talk about with regard to orthogonality. We're going to do one operation on the Fourier series that uses orthogonality to pick out a specific value of the weights and determine exactly what they are. So let's do that next. OK, now that we know a little bit about orthogonality, let's use orthogonality to make some progress on how we're going to find the weights. What we're going to do is multiply this entire equation by cosine m pi x over L and integrate. OK, so what I've done here is to literally take each term inside the definition of the Fourier series, multiplied each of those terms by cosine m pi x over L here, and integrated that between negative L and L. Everything in blue just came originally from the equation, and everything in yellow are the new things that I multiplied and integrated. So the left-hand side, shown here, is equal to a sum of 3 terms. Now we can start to make headway on what the values of these 3 terms are based on what we just learned about orthogonality. So let's first think about this first term. We have some constant, a0 over 2, which can be pulled outside the integral. So an integral of negative L to L of cosine function that has one full period oscillation between negative L and L. The area under the curve is 0. Because if there's one full oscillation, the lower lobe and the upper lobe, the positive and negative lobe cancel and get a net area of 0 under the curve. Just to convince you, let's do that. So we have here we have cosine m pi x over L integrated from negative L to L. This is equal to, apparently, 2L sine m pi divided by m pi. Now, sine of m pi. When m takes on integer values, which it must, sine of any integer argument, pi times that integer, is going to be 0 because sine passes through 0 every pi interval. So that means that this right-hand side is always equal to 0. Okay, good. So then what this means is that this entire integral is going to be equal to 0. Hold on, let's think about this. There's a special case when m is equal to 0. Because if you look at this solution here, when m goes to 0, the numerator goes to 0, but the denominator also goes to 0. So you have a situation where you have sine of 0 divided by 0. So the limit of that, you have to take L'Hopital's rule, so the derivative of the numerator and the denominator, right? And so when you do that, you're going to get a non-zero number left over. In this particular case, you're going to get 2L left over. Okay? So for this case, if m is equal to 0, then you would also see that because cosine of m pi x over L, for m being equal to 0, the cosine would just become 1 because cosine of 0 is 1. And so you're just integrating a constant from L to negative L. And so you get 2L to come out, which agrees with what we just showed using that Wolfram calculation. Okay? So if m is equal to 0, this term would survive. But otherwise, this would all go away. Okay? And that also is consistent with us throwing out the 0th index outside. Notice that the summation here goes from the index of 1 all the way out to infinity. So that's why the 0th index is treated a little bit separately. And this factor of 2 comes out precisely because the value we just showed here is equal to 2 times L. So the 2 cancels and you just get A0 times L. Okay? But suppose for now that we don't have the index of 0. If m is a non-zero index, then you can be convinced that this entire thing is 0. Okay. Now, the rest, pretty straightforward too. This second term, I just showed you a bunch of cases earlier, right? When cosine is multiplied with another cosine, it's always equal to 0 unless m and n are the same. When they're the same, it gives us L, just the domain size. So this whole thing, that integral, negative L to L of cosine m pi x n pi x dx, is equal to 0 when the indices are not the same, and L when they are the same. Finally, this third term down here, sine multiplied against cosine. We know from orthogonality that this is always 0, regardless of the value of n and m. I showed you test cases earlier. Okay? So what we get is a very interesting case where only when n is equal to m, one term survives, every other term dies, which is great for us because that means that we can uniquely calculate the value of that specific coefficient by performing the integral on the left-hand side. Let's make sure we both understand this. We have a summation here for the index n. That index n goes from 1, 2, 3, 4, all the way out to infinity. You've multiplied the cosine with the index m. That might be any value, might be 10, cosine 10 pi x over L. That's fine. This index n is going to cycle through 1, cosine 1 pi x over L times cosine, you got 10, so 10 pi x over L. That's 0. You do it again, cosine of 2 pi x over L times cosine of 10 pi x over L, also 0. You keep doing that because the index n takes on all integers. Eventually, it's going to hit the value of 10. So n is going to equal to 10. You get cosine of 10 pi x over L, cosine of m equal to 10 pi x over L. And that gives you L. That's it. So for whatever value of m it's taking, you're going to get uniquely only one value of the entire summation to pop out. Therefore, we can uniquely determine the value of a sub n. Let's write that down. Here, all I've done is to solve for a sub n when n and m are the same. So I'm no longer differentiating between m and n anymore because they're the identical number. And besides, n and m are dummy indices. You can choose any letter that you want. You can use Greek letters if you want. Any letter that runs through different integers. So we have simply L brought over to the left-hand side gives me 1 over L, the integral of negative L to L f of x cosine of n pi x over L dx. This uniquely gives me, for a particular value of n, I plug in cosine of n pi x over L, integrate, and this will just give me a number, right? I just have a one-dimensional function of x. I integrate between finite domains, negative L and L. Negative 2 meters to 2 meters of my room. They're specific numbers. So then the end result is that this whole thing will just give me a number, just some number. Pi, e to the 10, 1/3. It will just be a specific numeric value. And that's great because now I have a numeric value that tells me the weight of that particular cosine frequency or mode that I want that best models this function f of x. Now, this is how you obtain your coefficients for a sub n. Now, if you wanted to obtain the coefficients for b sub n, you can kind of imagine what you might do. You repeat the exact same calculation that we did, except you don't multiply with cosine m pi x over L. You multiply with sine m pi x over L. So you would replace these 3 instances of cosine with just a sine. And you repeat the exact same argument. And you can already see that in that case, the first term, the second term dies completely for all values of n and m. The third term survives only when n and m are equal to each other, which in that case gives you L. Therefore, you can uniquely obtain the coefficients or the weights of your sine terms by this expression right here. You have your left-hand side f of x multiplied this time by a sine function integrated from negative L to L. And this is how you obtain the Fourier series of a function f of x in one dimension. So the important equation to know are the following. Okay, so this boxed equation combined with this equation will allow you to determine the weights of each sine and cosine mode that you need to build up your function. With a basic understanding of Fourier series, a lot of you must still be thinking, what are you doing? I have no idea what's going on. And that's okay. That's how I felt too when I first learned Fourier series. What the heck is going on? It just all seemed like garbage. And why would you take a beautiful function like f of x and put it into this like garbage seeming thing of a bunch of summations and cosines and sines and frequencies? It doesn't make any sense. Okay, let's do an example for you to see how we might use the Fourier series for a specific function f of x. Let's do an example. Okay, so let's do an example. So far, the Fourier series, not really satisfying. A little confusing, actually. Majorly confusing because we have sines and cosines, we have weights, we have modes. What is going on? Let's do an example, and hopefully this will clarify some things. And let's do a relatively easy example first. Okay, suppose that we would like to develop a Fourier series for a very simple linear function f of x. F of x is equal to x. So this would just be a straight line that goes across the origin that has a slope of 1. Let's be proper with this. Get a straight line. All right, this is our function. F of x is equal to x. Now, we like to take this linear function and somehow piece together a bunch of sines and cosine waves in such a way that I could add together all of these waves, individual sines and cosines, to build up a linear function. Let's see what we would do. Now, the two boxed equations are the most important equations for us, so let's use those. We have some function f of x, so the left-hand side is x. We want to obtain the weights, the coefficients, a sub n and b sub n. Now we have two expressions here for a sub n and b sub n that we can now use. Now, the first coefficients are the a's, which corresponds to the cosines. We just take our function f of x, substitute it into this top expression, times cosine n pi x over L, integrated from negative L to L. Now, if you're really smart, you can find a very clever solution around this because you can see that x is an odd function between negative L and L, right? It's symmetric with respect to the origin, so it's an odd function. Cosine, on the other hand, is an even function, right? It's even with respect to the y-axis, and therefore it's an even function. An odd function times an even function is overall still odd, and an integral from negative L to L of an odd function must be 0, right? But just in case you're doubting me, let's go to Wolfram alpha and see if that gives us the same thing. There we go. We have integral of x times cosine m pi x over L from negative L to L is just equal to 0, as expected. So this one is always equal to 0, always. For all values of n, this is uniquely equal to 0. Now, the other coefficient b sub n, we can obtain that too, just like that. So I've taken our function, f of x is equal to x, sine n pi x over L, integrated from negative L to L. Now, this one, you can't use that trick as easily because they're both odd functions. The product becomes an even function. So now you're guaranteed that, well, you can't automatically say that it's 0 anymore. So unfortunately, you have to use integration by parts. Oh, yeah, I know. You have to use integration by parts. Call the two variables u and dv, integrate, you multiply across, you take the product, and then you integrate again. You should do that. I recommend you doing that. For the sake of this video, I'm going to skip that step and use this software. Okay. So integrate sine m pi x over L dx. Just to be clear, I'm going to shift that to n because we're also using n up here. We get this solution right here. Okay, it looks kind of weird, but let's think about it. So first of all, like I said earlier, whenever you see sine n pi, that's automatically equal to 0 because sine of pi interval, where n is equal to an integer, sine 1 pi, 3 pi, 2 pi, 5 pi, 10 pi, those are all equal to 0. So we know that that term must be equal to 0. But what about this first term? Cosine of n pi. Cosine of n pi is not 0 for integer values of n. When n is equal to pi, it's -1. When n is equal to 2, cosine of 2 pi, you're back at the origin, that's equal to 1, +1. So you go -1, +1. You go back to -1 again because sine of 3 pi is -1. 4 pi becomes 1, -1, 1, -1, 1. So it oscillates between -1 and +1. In fact, it oscillates like -1 to the n power. So we can actually write the solution to this, and it looks like the following. It looks just like this. So we had was the n pi out front that canceled the denominator, n pi squared. So I just have a linear n pi on the bottom. Upstairs, I have 2 times L, and that has an L squared, but that canceled out my 1 over L. So I just get a linear 2L. And then as advertised, what I have here is -1 to the n, but there's a negative sign out in front here. And that negative sign is just -1 to the 1 power. So I'm adding the exponents. So -1 to the n plus 1, it becomes n plus 1. Okay? If that was too fast, let me do a little quick thing here. So you know that cosine of n pi is equal to -1 to the n power. Okay? So if you have -1, which is what we have here because the integral here has a negative sign out in front, which is just -1 to the 1 power. This is just that, which is equal to n plus 1 power, which is we have right there. Okay. So what we find is that for the sine coefficients, for every value of n, it's whatever this number is. For b sub 1, I have 2L divided by 1 pi, -1 squared, which is just +1. And you keep doing it. N is equal to 2. 2L divided by 2 pi, -1 to the 3rd power, which is -1. Okay? And for all values of n, we're going to get some number to pop out. Right? So if we're given a domain size L, which is a number, pi is a number, you have a number that comes out. Okay, so now let's plot this and see what it really looks like graphically. Because at this stage, it's still kind of garbage to me when I first learned it. I was like, okay, A's are 0, Bn is this crazy thing, and then you have this summation. It's still confusing. Let's plot this and see how it looks. So what I have here is a MATLAB code where I've just coded up the solution that we got. So we have here is I'm defining how many terms in the summation I want to take. So up here what we have is an upper limit of infinity, but practically in any application, you can't take infinite number of terms, so you take a finite number of terms. So n goes from 1, in this case, to some number of terms that you can define. For now, I've set it equal to 5. So I'm just going to take 5 terms in this summation. And here I've defined the function Fourier series, where here I'm summing over the terms. And right here I have b sub n, which is equal to exactly what we have written right here. -1 to the n plus 1 power times 2L divided by n times pi on the denominator. And I'm going to take that coefficient and multiply it with sine n pi x over L. Just coming from right here, right? I have this b sub n that I'm going to plug here. So essentially what I'm doing is I'm going to take this guy, bringing it right there. That's all I'm doing. And of course, this, for our current application of the linear function f of x equal to x, is equal to 0. So all I have is just this term with these coefficients. That's what I've coded right here. And I'm adding it to a value of fs, which just keeps adding the numbers because it's a for loop. You just keep adding more and more numbers. And this is exactly, you're doing summation. This is summation in the language of coding. And all I'm going to do is plot it. So you don't really have to focus on the stuff down here. That's just plotting. So I'm going to execute this. And it looks something like this. What we have is, again, the function f of x is equal to x, bounded from the value of negative L to L. In this particular case, I've defined my length to be 1. So it goes between negative 1 and 1. And it repeats. It's a periodic system. Okay, so it goes from negative 1, it jumps back up to 1, and then it forever repeats onto infinity. Okay, so but we're only interested in the domain of negative 1 to 1, negative L to L. You can see that this black line is the original function f of x is equal to x, the linear function. This red curve is our approximation of that function linear x, where we've taken 5 terms. So right here in this expression, we've taken b1, b2, b3, b4, b5, multiplied with sine 1, sine 2, sine 3, sine 4, sine 5 of those respective indices, slapped them together, and then plotted it. That's what you see in the red curve. You can see that it does a pretty crummy job. I mean, if you just show me this red curve, I'd say get out of here. That looks nothing like the linear function f of x is equal to x. So we've only taken 5 terms. And the Fourier series is exact as the limit goes out to infinity, but if you truncate it to a finite value, it's only going to be an approximate now. So if I take 10 terms, you can see the dramatic difference. You can see that the function is much closely approximated by the Fourier series with 10 terms. Now I've taken sine 1, sine 2, sine 3, all the way to sine 10. We can keep going, and I can do sine of 50, for example, and it's even better now. You can really see how effective the sine function is converging to this linear function f of x equal to x as we add more and more terms. Now, I wanted to mention a couple of things. First, you notice that we had to take 50 terms. And in fact, it's still not perfect. You can see in this function that it still doesn't converge in certain regions as well as you might expect it to. And the reason why the convergence with even 50 terms is so slow is because this coefficient up here decays like 1 over n. That's actually a killer. It's a very, very slow decay. It means that if I take 10 terms, I have roughly 1 over 10, so that's 0.1, a 10% error. If I take 100 terms, I still have roughly a 1% error that I'm neglecting if I don't include the 101st term. So it's a very, very slow decay in the weight of my coefficient. That means I need to take a lot of sine functions added together to closely approximate my function. Ideally, I would have a coefficient that decays more steeply with n. For example, it might be 1 over n cubed. That would be amazing if it was 1 over n cubed scaling, because that means that if I take 10 terms, I have 1 over 10 cubed, which is 1 over 1,000, so 0.1% error. That's pretty amazing with just 10 terms. And the reason why this is so slow is that it turns out polynomial functions are extremely difficult to model with the Fourier series. It's kind of weird, but simple function, something as benign as f of x is equal to x, is actually kind of difficult to model using sines and cosines. Because sines and cosines are curved, it's periodic. F of x equal to x is sharp, it's cusped, it has a jump at the edge. And so it's actually very challenging to model straight lines that look something like this. And that's why polynomials are actually very difficult to model using a Fourier series. Now, the second point I wanted to make is that you can see here that at the boundary, right where it jumps, you see an overshoot. This is called the Gibbs phenomenon. It turns out that no matter how many terms you put in there, you will always see this jump. You will never get the jump to go away. For example, let's take, I don't know, will my computer cry if I do 300 terms? Oh, it's not going to cry. Good. So now the function is very well approximated all the way through, except near the jump. You still see an overshoot, a ringing right at the jump. And the reason why this happens is a very fascinating one. It's called the Gibbs phenomenon. It turns out that the Fourier series converges with an L2-like norm. What it basically does, it has some function, f of x. It takes the difference in the approximate solution with the actual solution, square that, and take the area under the curve. It's like least squares error, L2 norm. That goes to 0 as the upper summation limit goes off to infinity, because even though the overshoot is still there, that overshoot is getting pushed and wedged to closer and closer to the boundary edge of L equal to 1. So while the overshoot is there, that's getting smaller and smaller and smaller and converging to epsilon all the way to 0 as you take more and more terms. So the error overall is still going down as you increase the number of terms, because you're just pushing that overshoot closer and closer all the way to the boundary. And that's why the Fourier series converges, even though there's an overshoot that exists here. And also, the reason why the overshoot exists here is that the sine function is a periodic function that has to go from a value of 1 all the way back down to -1, because it's periodic. So it goes up and then boom, oh no, I gotta go all the way down. But to go all the way down, a sine has to use a high frequency thing to curve around. And so it can't just bluntly stop and then turn back the other way. It's curvy, so it goes and overshoots and then it curves down. And that's why it overshoots. Okay? It's called the Gibbs phenomenon. It's a fascinating process. Okay, so hopefully you got an idea of how one would use the Fourier series to approximate functions like f of x equal to x. You might still be wondering, oh my gosh, why did you take this beautiful function f of x and erode it into this disgusting summation? Why would you ever do this? Why would we ever need this in science and engineering? Why would you take this beautiful function of f of x equals x and rewrite it into this disgusting looking function? Well, hold on to that thought, because next we're going to do partial differential equations, and this is going to come to our rescue. There's one more thing I want to talk about at the very end related to sine and cosine extensions. So let's talk about that. Now, one last subtle technical detail. In many situations in science and engineering, we don't have a domain between -L and L. We might have a heat exchanger or reactor that's bounded between x of 0 and x of L, only along the positive domain from 0 to L. Well, every definition we've created so far is a Fourier series that's periodic from -L to L. So how do you reconcile this difference? How do you take a function from 0 to L that's defined there and extend it backwards? This is the concept of a Fourier sine or cosine extension, or an even and odd extension. So using our example from earlier, f of x equal to x, suppose we were only define that function from 0 to L. We want to figure out how to create the sines and cosines of that function from 0 to L only. Well, like I said, under the hood, we need to develop a Fourier series defined from -L to L. So you have two choices. You can either expand this function in the following way, like that, where you just cut right through the origin. Okay? from negative L to L, just go right through it, or you can reflect it about the y-axis, just like that. So in either case, you're only interested in modeling the domain 0 to L, okay? But under the hood, you're actually extending it either in an even fashion or an odd fashion. You either reflect it about the y-axis, it's an even function, or about the origin, which gives you an odd function. So now the difference is that the Fourier series actually differs now. Earlier, we did the y, the f of x equal to x from negative L to L, and only the sign stayed, because we made that argument about how you're multiplying an odd function with a cosine even. That was all gone. So a's were 0, you only got b's left over. So over here, you're effectively doing what's called a sign extension or an odd extension. If, for example, you were to do an even extension, things are slightly different because now it's an even function. And that argument we made earlier about, okay, you're going to take the integral f of x equal to x, multiply it with an odd function. Now look, you have an even function times an odd function. So now your b's are equal to 0 and your a's are non-zero. So it flips. So now you just get a cosine series because you've made an even extension. Okay? So practically, you only care about modeling 0 to L, and no matter which extension you use, it will both work. In one situation, you'll come up with a series that looks like this, exactly what I showed you in the example. But in the even case, you'll get a Fourier series that looks something like this. Between the domain 0 and L, they're both going to approximate the function very well as you take the number of indices going out to a larger and larger value. And when we start using Fourier series to solve partial differential equations, you're not really going to get that choice. As you will see, whatever initial condition you have will dictate whether you are taking a sine extension or a cosine extension. You will see that it will naturally be determined for you, so you don't really get a decision to choose whether you do an odd or an even extension. But outside of solving partial differential equations and the heat equation, diffusion equation, if you have a choice, if you happen to have a choice in an even or odd extension, one consideration to make is the Gibbs phenomenon. So remember, in the odd situation, the example we just did, there's a huge jump that happens right at L. There's an overshoot that happens right at the boundary because it's periodic. But look, for the even extension, you're not going to get that significant jump discontinuity at L equal to 1. And because it's periodic, it's just going to look like this. Okay? So the jump discontinuity at the boundaries will be one consideration to think about when you have, if you have a decision to use odd or an even extension. Okay, with that, I hope you understand 1D Fourier series. And next time, we're actually going to talk about how Fourier series can be used to analyze images in 2 dimension. Have a good day and see you next time.